And we're back again. We are still in Calculus BC, contrary to what this might say up at the top. This is our second day, and it's a bit of an extension of what we did the first day. So we got the idea, the theory behind integration by parts on the first day. Today we're going to explore two additional concepts, both which fall under that same umbrella. Just a couple example problems, I think, and then you'll have a bunch of practice problems at the end as before. So let's see, what do we have? 2 pages here, and then the practice problems, there are 5 or so good practice problems, and the solutions again are posted on Microsoft Teams, so you can take a look at those. So let's go ahead and start working through. Your goal is to evaluate the following integral, and hopefully you are comfortable with that LIPIT acronym at this point, so let's see how that goes. We'll write this over on the side so we can keep track. Are there any logarithms in here? No. No inverse trig. No oh, there is a polynomial. X squared is a type of polynomial, one where when you take the derivative, it gets nicer. So let's go ahead and maybe keep track in a nice little chart over here. We're going to say that our U substitution will be x squared, which implies that our du is going to be 2x dx. Sweet! Of course, if that is our u, then we know for our integration by parts, this has to be my du. So my du is e to the x dx, and so now we work backwards. I'll show the arrow going the other way, and that tells us the antiderivative of e to the x dx is just e to the x. Okay, got our u, du. Let's see what happens with this sweet integral. I'm actually, knowing where this problem is leading, going to start on the left side. So again, I always like to write out the integration by parts formula. Integral of u dv is equal to u times v minus the integral of v du, and then we fill things in. Original problem first, so that was of course our x squared, and then what do we have over here? Our v or our u. Oh, I said du up there. Haha, that's a dv. vu, silly variables. Okay, is going to be, of course, e to the x dx. That's our original problem. Equals, let's fill in these couple pieces. Here we go. U is again x squared. V, the antiderivative of dv is e to the x. V again is e to the x, and then du is 2x dx. Okay, well, at this point, I actually don't think there's too much we can do here, because we have, of course, the original problem, always keeping it on the left, and then x squared e to the x. I can factor a 2 out of here, but then that leaves me with x e to the x dx. So how do we do the antiderivative of this? Well, hopefully you're looking at that going, wait, that's the problem you tried to trick me with yesterday, but we learned how to do it yesterday. And we learned how to do it by another U substitution, right? This is, or another integration by parts, a double U substitution. Ironically, it's not W though, it's U and V. You get the idea, it's a good joke. So we have these two multiplying. Okay, well, what do we do with that? Well, let's do another u and v substitution. Now, since we already used u and v, we should probably pick 2 other variables. I'll do a and b. Why not? And I'm actually going to do this problem over on the side because I like to keep my work continuous going down here. I want my very next step here, x squared e to the x dx equals x squared e to the x minus 2. I want my very next step to actually be the answer to this. So let's see what happens here. And you could show all of this in one step if you wanted. We have enough room. Let's go wild. Here we go. So we need to split this up. It's going to be the same split that we did for the original problem, except I'll use a this time. We're going to say a is x, which means that dA is 1 dx. And then, of course, that leaves the rest of this to be dB, which is e to the x dx, and if we work backwards, that tells us that b is just e to the x. Okay, so let's use our integration by parts formula. Okay, our integration by parts formula tells us that this guy is going to get expanded out, and it's a little tricky here, so make sure you follow along, and I'll write the letters up above just so we can keep track. Remember, it's u times v minus the integral of v du, right? That might help you out. So u in this case, or, it's a, isn't it, right? A in this case is x, and v is e to the x, minus the integral. V again is e to the x, and u is 1 dx. So we took what was in there. Couple things to note. First, Please notice that I used parentheses here. The parentheses are really going to help us group everything together so that we don't lose that -2. And second, we are still not done because we still have an integral. However, this is much easier now. So let's see, I'll keep that, I think, -2 on the outside for now. You could distribute it first if you wanted. Again, I'm taking the time to rewrite the original problem. This isn't going to change anywhere, but we can do the antiderivative of all this. It's just e to the x. We don't need the 1, so that's looking pretty nice. And now let's finish it off. X squared e to the x dx is equal to x squared e to the x minus 2x e to the x plus 2e to the x. You could, of course, factor out an e to the x out of all of this if you wanted. That'd leave you with x squared minus 2x plus 2. Maybe that looks a little nicer than what we started with. And we are, of course, done. You could have also stopped here. So this is a double integration by parts. It's also pretty commonly taught to do integration by parts in a tabular method using a table. I'm not going to go into that. And the reason why is that I think if you do integration by parts once, you can do it twice. A table is just one extra thing to memorize. If you'd like to learn it, and it is kind of a cool method, just Google integration by parts tabular or table method, and you'll see it there. And I've seen it on past AP exams, nothing wrong with it, but here's the thing. Integration by parts only comes up 1, maybe a maximum of 2 times. Learning yet another method to do it isn't really going to help you. So, just a little generalization then. There are, of course, times where you have to use integration by parts more than once. We just saw that. Those most commonly occur if you have x to the n power times something else. And that should make sense because if you do your first U substitution, that's x to the n, then du becomes n times x to the n minus 1. The power gets 1 smaller. And if you keep doing that over and over again, eventually your du is going to turn out to be 1, right? There might be a number in front of it, but eventually it's going to turn out to be 1, and then you'll have simplified the integral enough, if there's a 1 in here, that you just do the antiderivative of the trig function or the exponential. So again, you might see that x to the n power is usually a good giveaway of how many times you have to do it. If this problem was x cubed times e to the x, we'd have to do integration by parts 3 times, and so on and so forth. However, I don't think any of the problems you see down below or that we do today, you'll have to do integration by parts more than twice. I threw in this example because I thought it was a cool one. However, it's not one you'd be expected to do. But this is just a little bonus of how to take the antiderivative of natural log, because that comes up a bunch in Calc AB. And I always try to trick you guys, and I say, oh, what's the antiderivative of natural log? And you're so clever. You're like, oh, it's 1 over x, oops, plus c. Wow, I am out of practice. I forgot the plus c again. Somebody fire this calculus teacher. Okay, so either way, mas say, very nice. So I always try to trick you guys with the antiderivative. You're like, oh, it's 1 over x. I'm like, not quite. If this said d dx, if it was the derivative, it'd be 1 over x. But we talk about how we can't, in air quotes, find the antiderivative, and I'm very careful to say can't find it yet, because in BC you can. And the way you do it is by integration by parts, and that's a very clever integration by parts. You're like, by parts, but there's no part here. Well, if you put in a times 1, now we do have 2 equations here. This one also does follow Lipit, which is kind of cool. So Lipet, we look for our U substitution, and we're like, well, is there a log in the problem? Oh, there is. So that should be the U substitution. And again, the idea behind your U substitution is you want to take a piece that will simplify down. Now, you might have been tempted to say, well, 1 simplifies down to 0. That's true, but then you're still going to be left with a natural log somewhere, and so life's going to get complicated. You always want to pick something that will simplify a complicated piece. The rest isn't too bad. dv, antiderivative is x, and so then we do the u times v, which is right here, minus the integral of v du. But then v du, this is pretty cool. X times 1 over x just becomes 1. So then when you do the antiderivative of 1, it's x, and you've got your antiderivative of natural log, which is x times the ln of x minus x. Could you check to make sure that was the right answer? Well, of course, you would just take the derivative of x times the ln of x minus x. You'll have to do the product rule here, right? Don't forget that. And then the minus x at the end becomes minus 1. Things will cancel out, and you'll be left with natural log. All right, last part of this. This is nothing new either, but hopefully it will stop me from forgetting to write plus c because we won't need to write plus c here. So we've done indefinite integrals all the way through. We're going to do one example of a definite integral. With our definite integral, it's going to be very similar, but when you do the antiderivative, you actually need to remember to plug in the endpoints to uv. And then, of course, when you do the antiderivative over here, you'll also have to do that fundamental theorem of calculus and evaluate at the endpoints. So let's do a very similar problem to the example up above. This is our natural log of x. We're going to be clever here, and we're going to put in, I don't know why I put an extra times there, we're going to put in that times 1 dx. Let's go ahead and practice our U substitution. We already said U would be natural log, which makes du equal to 1 over x dx. And working the other way, that of course means that dv is 1 dx. And when we do the antiderivative, it becomes x, right? That's v. There we go. Okay, let's work this through then. So we have the original problem, the antiderivative from 1 to 2, that definite integral of the interior, right, the integrand, and we go through and we work our magic. So it becomes u, which is natural log of x, times v, which is x, okay, evaluated from 1 to 2, minus the integral from 1 to 2 of v du. Let's keep working through, keeping that left side constant, though I'll toss out the 1 because it's one fewer things to write. I actually tend to not do the fundamental theorem till the very end. I like the other part to catch up. That's personal preference. You could evaluate this part out. Don't forget that this just becomes 1 right here, though. So the antiderivative of 1 is x, and then evaluated from 1 to 2. Again, I like this one a little bit nicer just so then we can get everything working. So let's finish this off. Fundamental theorem, hopefully we haven't forgotten too much. We of course do the top value first, natural log of 2 times 2 in parentheses, minus the natural log of 1 times 1, minus, and then same thing over here, 2 minus 1. Okay, let's keep working this out. Natural log of x dx equals, well, this is just 2 ln of 2. Any log of 1 is 0, so that'll become 0. And then this piece is just a 1 with the minus that's over here. So I think we just end up with minus 1, and we have our value. Okay. So again, that's all we have for you. There are a couple tricky problems down here. Our first one, we see that x squared, that probably means integration by parts twice. But a lot of these are tabular, and you'll see most integration by parts problem on the AP exam looking like this. Instead of them giving you an actual function here, they'll give you values of functions. Still think about Lipit. If you can, think about what's going to be easier versus more complex. So for example, on this one, you have a couple options. Maybe you think that your U substitution is f double prime, okay? But then your du is going to become f triple prime, and you don't know anything about f triple prime in the table. So my guess is we probably went the wrong way. I bet our U substitution here would be 1, or would be x, and then du becomes 1 dx. And that holds with Lipit because it's simplified x to 1. F double prime, when you take the derivative, it doesn't get simple. It probably stays about the same, but especially because the table doesn't have f triple prime, probably not a good substitution there. Okay, same idea down here. We probably don't want to do a u for g double prime because then du would be g triple prime. 4 is a particularly tricky question, and you might need the solutions to guide you. And then 5 is nothing too terrible. So these tabular problems, again, are common because these are problems that you can't plug into your calculator, right? Your calculator needs a function. You can't just plug in f of x. It's going to say, well, what is f of x? So you'll see these, and a lot of times they'll be used as fillers on the calculator active section, too. They might try to trick you up. I think in particular some of these came from the late calculator active sections. So just be ready for that. If you need help, reach out to me. Check out the solutions that are over here. If you have a faster way to do it or you look up the tabular method, Good on you. There's nothing bad about that. We'll come back next class for our partial fraction decomposition.